Hello, my name is Cade Bogan, and in this video, I will be going over my research paper on lithium iron phosphate batteries. To begin, I will be doing a brief overview of lithium ion batteries and then jumping straight into lithium iron phosphate batteries. Lithium ion batteries are a staple in the rechargeable battery world. They are also called secondary batteries, which means they are capable of being recharged, not to be mistaken with primary batteries, which are only capable of being charged at a single time. The first model for a lithium-ion battery was developed in 1985 by Akira Yoshino using research from John Goodenough and Michael Stanley. The three of them were later awarded the 2019 Nobel Prize in Chemistry. While there have been many advancements in lithium-ion batteries, the four main components remain the same. This includes the cathode, anode, electrolyte, and separator. The differences in these components is what makes different lithium-ion batteries. More specifically, the cathode is what makes the greatest change in the lithium-ion batteries. Lithium cobalt oxide, lithium nitrogen oxide, and lithium manganese oxide are some of the most commonly used cathode materials, but we will be focusing on lithium iron phosphate for this video. The use and advancement of lithium iron phosphate in batteries will be critical for the advancement of our electric society. John Goodenough, alongside his partner Arumugam Manthiram, would diverge from the traditional use of oxygen anions in cathode materials and would explore the polyanion class of cathode materials. They proposed that a series of iron compounds could help remedy some battery issues at the time, such as structural instability and poor electron transfer. Lithium iron phosphate was discovered to fit this criteria by Akshaya K. Paddy in 1996 and was demonstrated later in 1997 by Goodenough. With a specific capacity of 120 to 160 milliamp hours per gram and a theoretical specific capacity of 170 milliamp hours per gram, lithium iron phosphate is more than capable to hold charge for various electrical devices. And while some lithium ion batteries hold more charge when factoring in its cycle life, durability, and the material used for it, it is more than a contender for lithium ion batteries. Diving into the components and the structure of lithium iron phosphate batteries, we first look at the anode, electrolyte, and separator. These remain largely the same throughout all lithium ion batteries. The anode is made of graphite powder placed on a thin layer of copper foil. When discharging lithium iron phosphate battery, lithium ions move from the anode to the cathode, and electrons move from the anode to the cathode as well. They end up in the same destination, but they do not follow the same path, as electrons do not flow through the electrolyte. The separator keeps the electrodes apart. Without the separator, there would be no potential difference, rendering the battery useless. The electrolyte allows for the flow of lithium ions while also preventing electrons from flowing within the battery. It is normally made of salts, solvents, and additives, and can be either solid or liquid. There are advancements being made towards solid electrolytes, but at the moment, liquid electrolytes are the most prevalent. Lithium iron phosphate is an inorganic chemical compound that is found naturally, but the powdered form is used in production of lithium iron phosphate batteries. This cathode material is applied in its powdered form to a sheet of aluminum foil. Being part of the olivine family, it is especially efficient at intercalating lithium ions into either the iron phosphate or the graphite. And when completely discharged, lithium iron phosphate batteries, in theory, should have no lithium in the anode. When discharging its stored chemical energy, lithium iron phosphate batteries move from the anode to the cathode. As stated previously, this is done by deintercalating lithium from the graphite and moving it to the cathode. When charging, lithium ions undergo intercalation with the graphite anode, moving lithium ions into the graphite, becoming lithiated graphite. In this image, we can see this process with the negative representing the anode, the positive representing the cathode, and a power source, which is not depicted here, somewhere off to the side. Wires would connect the anode to the power source, and wires would connect the power source to the cathode. Lithium ions are seen moving from the anode to the cathode here, and all of the other components are shown as well. Now, there would not be a case for using lithium iron phosphate if there weren't some advantages, but seeing as it is not currently the most predominantly used lithium ion battery, there are some disadvantages as well. But to start with the positives, it is non-toxic and environmentally friendly compared to cobalt, which is a necessary element of lithium cobalt oxide batteries. It is thermally stable, as it is bound together by covalent bonds, which is the strongest type of bond. It also has a low resistance to the electrolyte and a high electric conductivity, which allows for a smooth transfer of lithium ions. It is also relatively cost efficient, which should be very clear as to why that is important. These advantages make lithium iron phosphate particularly useful in the storage of renewable sources of energy, as well as in electrical vehicles. This is because heat can build up, but with the thermal stability of lithium iron phosphate, it is more than capable of bearing that load. In this table, we can see some different types of lithium ion batteries, with lithium iron phosphate being at the bottom. It does have a lower specific energy than all of the other lithium ion batteries, but it makes up for that with a significantly higher cycle life, a higher durability to high temperatures, and a low production cost. That is all for this video. Thank you for watching. Have a good day.